Good morning. Welcome to lecture 4 of unit 1, and in this lecture we will be talking about Fourier series and related expansions. So, this is the outline of this lecture. We will first talk about the Fourier series, and from Fourier series we will learn about T space truncated sinusoids expansion. Then we will talk about discrete time Fourier transforms, and from discrete time Fourier transforms we will learn how to do these T space sinc weighted sinusoid expansions, and then we will also learn in this lecture about sampling theorem. So, this is the outline of the lecture, but let us first recap what we have learned in the last lecture. We have started with the idea of Gramschmidt orthogonalization procedure. Using this procedure, if we have signals, we can convert these signals into vectors, and what we needed to do is to find out the basis functions, and we have to find the coefficients of these signals along those basis functions. Okay. So, this is one big thing that we learned. Then we have also studied about the transmitter design. So, transmitter converts sequences to waveforms. So, we said that if we have a sequence, what we can do is we can multiply each element of the sequence with orthonormal basis function, and we can sum up all the products of this multiplier. So, from this we get a signal. So, there were sequences here, and from the sequences we can get a waveform. Similarly, we have looked into the receiver design, and in the case of the receiver design we said that if we are receiving a waveform, we can pass this waveform through what is known as correlator, and at the output of the correlator we will have the projection of this waveform along this orthonormal basis function. Okay. So, then we can obtain a sequence corresponding to the received waveform. We have also said that instead of this correlator, which is made up of a multiplier and integrator, what you can also do is have a meshed filter. So, meshed filter is a filter whose impulse response is matched to orthonormal basis functions. Okay. So, you need to use bank of meshed filters or a bank of correlator. From theoretical point of view they are similar, however, there are some practical differences. Then we have looked at the full blown receiver implementation, where the receiver first produces the sequence corresponding to the received waveform, and then it does the inner product of this received sequence with the sequence of the signal set that it has. Resultant is that it calculates the inner product of the received waveform with various signals, right. And we have said if these signals are not of equal energy and they do not occur with equal probability, then normally you also have to add some bias. Okay. So, then at the output of this, so based on the output of this point, whichever produces the largest output, receiver assumes that is the transmitted signal. For example, if I have the maximum output from this branch, then the receiver would select S1 as the transmitted signal. So, this happens in a receiver implementation. Why do we add this bias and so on and so forth? These things will become clear when we will go into the regime of detection. At this point, it is important to appreciate that at the receiver as well as the transmitter, the important operations that happen is the inner product. Okay. Okay. So, in today's lecture we will be talking about other forms of orthogonal expansions, and these forms of orthogonal expansions can be arrived by using the principles of Fourier series or Fourier transforms. So, let us start, and let us start with Fourier series. So, we are starting with Fourier series. You must have studied this Fourier series in a basic course on signals and systems. So, we are not going to dig deep in this Fourier series. I would be just revising what you have learned and maybe adding some flavor to this Fourier series based on what is important in the context of digital communication. So, what you must have read in Fourier series that if you have a signal x t which is periodic signal with period t, then you can express the signal by using this expression. So, here A k's are known as the Fourier series coefficients. Okay. And what is this omega naught? Omega naught is 2 pi by t. Now, you must have also studied that if you want to obtain this a k, we can find out this a k by carrying out this integration. Okay. Now, this is what you must have studied. If you have forgotten about this, do not worry, believe me that these expressions are used for the expansion of a periodic signal, and if you want to derive Fourier series coefficients, you can derive them by evaluating this integration. We will also understand later on how is this related to orthogonal expansion. But one thing that we like to start with is, if this x t is a periodic signal, if x t is periodic signal with period t, then this signal is useless signal from the point of view of communication. Why is this useless? Because by periodic signal I mean that the signal repeats itself after a time duration of t seconds, and if the signal repeats itself after the duration of t seconds, then there is no information contained in that signal after t seconds, right. So, why would any communication engineer would be interested in such a signal, right. So, such signals, periodic signals, are not important from the point of view of communication. So, when we are trying to define Fourier series, we would define it in a slightly different way than what you have studied in signals and systems. What we will be saying is, suppose I have a periodic signal, I am not interested in this part of the signal, because this part of the signal has the same information as this part. So, what I am interested in is trying to find out the expression for a signal only contained in one time period. For example, I call this one part of the signal as x t. So, when I am saying x t now, from now onwards, it would mean that this is the signal that is present only in one time period. And let us also say that this, let us assume, goes from minus t by 2 to plus t by 2. Now, this signal x t can be obtained by multiplying x p t, where p denotes that this is a periodic signal. So, subscript p will tell you that this is a periodic signal. So, x p t is the total signal, right. So, if I am interested in x p t, it is the whole signal which is a periodic signal. So, if I have a periodic signal and if I multiply this periodic signal with a suitable gate, so here I have multiplied it with a rectangular function. So, rectangular function is defined. So, rectangular function rect of t by t is 1 for t between t by 2 and minus t by 2, and it is 0 otherwise. let me draw the picture of rectangular function. So, this rectangular function would look like this. So, it has a value 1 for time duration between minus t by 2 to plus t by 2, and everywhere else this will be 0. So, once I multiply my xpt with this rectangular function, what it will do is it will only give me the signal contained in this time duration or in just one period, where the period spans from minus t by 2 to plus t by 2. And thus, I can obtain the Fourier series for this x t, where x t is now not a periodic signal, x t is an aperiodic signal. So, I can write the Fourier series expansion for x t as a k times e to the power j k omega naught t, because this is what is x p t, and I can multiply this with rect t by t. And of course, I need to have k going from minus infinity to plus infinity. Sometimes I may not write that the limit of k is from minus infinity to plus infinity, and then you should understand it as that k takes all possible values. So, what I am saying is, because the communication engineers are only interested in aperiodic signals, and if I have an aperiodic signal which is limited to the time duration of t, I can obtain the Fourier series for this signal by using this expression. For all values of k. Okay. How can I obtain a k? A k can be obtained as before, right? The expression of a k would not change. Okay. Let us now try to understand this from the orthogonal expansion idea that we have just seen. So, if I can write x t as sum of a k into phi k t, I know that we can write this if phi k t's are orthogonal functions, or these are the signals from the orthogonal set. And what are these a k's? A k's are nothing but they are the coefficients of these orthogonal functions. Okay. Now, the Fourier series also looks exactly similar to this. So, let me write again that expression. Where I can say or consider that this is nothing but phi k t. So, if I consider this signal as phi k t, these two expressions look exactly same. The only thing that now I have to prove is that this signal is the signal from the orthogonal set. That means, this phi k t or the set corresponding to phi k t is an orthogonal set where k belongs to set of integers. So, this is what we have to prove. If we have been able to prove that this is an orthogonal set for k belonging to set of integers, then we can say that Fourier series is nothing but it is the orthogonal expansion of a signal. And how do we prove that something is orthogonal? We take the inner product. So, if I take inner product of phi k t with let us say another signal from the set which I call as phi m t, and if I can prove that the inner product of these two signals is 0 if k is not same as m, then we can say that these signals are orthogonal signals. Of course, if k is same as m, then this is the inner product of the signal with itself and it will not be 0, but it will correspond to the energy of the signal. So, this is what we have to see. Okay. So, phi k t here is nothing but it is e to the power j k omega naught t rect t by t. If I take the inner product of phi k t with phi m t, this inner product would be defined as, so first I have to have phi k t multiplying this with conjugate of phi m t dt. So, this will correspond to the inner product of phi k t with phi m t. I can absorb this function in the limit of integration and this will then become, the integration goes now from minus t by 2 to plus t by 2 e to the power j k minus m omega naught t dt. And let us now see what is this. So, we start thinking about this by considering the easy case first. So, we have case 1 when k is same as m, when k is same as m, this function becomes 0. So, this part becomes 0. So, we have e to the power 0 dt, e to the power 0 is 1. So, we have, so this is going from minus t by 2 to plus t by 2. So, we have t. Okay. So, when k is same as m, the inner product of phi k t with phi m t is t. Now, let us investigate the second case, case second, when k is not same as m. So, let us assume that k minus m is another integer n, k is an integer, m is an integer. So, k minus m will be n. So, this will become e to the power j n omega naught t dt. Now, instead of thinking this in terms of complex exponential, let us use Euler's theorem and break it into sinusoids. So, I can think about this in this way. So, using Euler's theorem, I can write this as cos n omega naught t plus j sin n omega naught t dt. Now, if you look the time period of this signal, the fundamental period. So, if you look, the fundamental period of this signal is t by n. The fundamental period of this signal is also t by n. That means, in this limit of integration, this cos and sine will make n cycles. Okay. So, that means if I am interested in the period of integration which is t. So, let me take the example of a time duration t. So, let me assume that this is my time duration t. So, in this period the sinusoids will complete integer number of cycles. So, let us just do it for sine. So, for example, the sine will make integer number of cycles, in this case this integer number is 2. What we have to appreciate is if a sinusoid function makes or completes integer number of cycles in the period of integration, then the area under this function is always going to be 0, because the positive part will always cancel out the negative part. So, if I am integrating a sinusoid function and if that sinusoid function completes integer number of cycles in that period of integration, then the integration of that sinusoid function would be 0. Okay. So, what we can now understand here is that this integration would give us 0. So, now we can summarize that if I am carrying out the inner product of phi k t with phi m t, that means I am interested in carrying out this integration, then this will be 0 when k is not same as m, and when k is same as m, this is going to be t. And hence we can say that phi k t, the set phi k t where k belongs to set of integer, is an orthogonal set. Okay. Now, let us try to find out, can we find out a k's from x t. So, let us just carry out the inner product of x t with phi m t and let us see what this gives us. So, if you do this inner product operation, so x t we know is a k e to the power j k omega naught t into rect t by t, and I am interested in carrying out the inner product with phi m t. So, inner product is nothing but you have to take the signal and you have to multiply the signal with the conjugate of another signal. So, phi m t's conjugate is e to the power minus j m omega naught t. It also has this rect t by t dt, and again from Fourier's theorem I can change this order of integration and summation. So, what I get is a k integration of e to the power j k minus m omega naught t. I can absorb these rectangular functions again in the limit. I get this, and this quantity we have already said is non-zero only when k is same as m. So, we can write this as, we have a k's, and instead of this we can express this as t times delta k minus m, where delta is an impulse function. So, this will mean that this is only non-zero when k is same as m. When k is same as m, it is 1 and it is multiplied by t. So, this is exactly what this integration will lead to. Okay. So, now when k is not same as m, this will give you 0, and so in the summation there will be no contribution from other terms except a m. So, I have just a m t left, because this will make all coefficients other than the coefficient a m effect to be 0. So, then what I am saying is inner product of x t with phi m t is a m times t, and from this I can say a m is nothing but 1 by t inner product of x t with phi m t, and which is 1 by t x t, phi m t is e to the power minus j m omega naught t rect t by t dt. So, this is a m. So, we have minus here because we are taking the inner product, and so this minus comes because of conjugation. So, we have learned the Fourier series, and let us recap the major ideas that we have developed. So, what we are saying is we can express a signal x t in terms of orthogonal functions phi k t. We have proven that this is a set of orthogonal functions if k belongs to the set of integers, and these orthogonal functions are this, and in literature this is also referred to as truncated sinusoid. This is a sinusoid, and this truncates this sinusoid to one time period. Okay. So, these phi k t's are also referred to as truncated sinusoids. You can obtain these a k's just by carrying out the inner product of x t with phi k t and dividing it with the energy of phi k t, and that is t. Okay. So, now we have seen that this Fourier series is nothing but it is the orthogonal expansion of a signal. Is this of any use? Let us see it now. So, in practice what would happen is the signals in which we were the signals in which we are interested in will be of a pretty long duration. Okay. Let us say this signal spans a pretty long duration, and we say this as T L. Now, if you have to wait to process the signal, or if you have to wait to receive the signal for for a time duration of T L, then only you can calculate these a k's, and then only you can transmit these a k's. This will create lot of delays in the communication system. So, one idea is that if you have a signal, instead of waiting for the entire reception of the signal, you can break this signal into segments. So, I can take a segment of these signals. For example, in voice applications, the duration of the segment is typically chosen to be 20 milliseconds. And then I find the coefficients corresponding to a segment of a signal. So, this is the segment 1, 2, 3 and so on and so forth. So, if I pull out a segment, let me call this as x 1 t. This segment x 1 t can also be thought as it is constructed from the periodic signal x 1 p t. So, x 1 p t is a periodic signal. If you multiply this periodic signal with a gate, so if we multiply this periodic signal with this gate, we can get this segment. Now, similarly, I can think about the second segment, which again I think in the same lines as if it is constructed out from the second periodic signal, and by multiplying this second periodic signal with a gate, but now this gate would be shifted by t units, because this second segment, this one, is t spaced from the first segment. So, you need to choose a gate which is non-zero in this duration. So, in a duration between t by 2 to 3 t by 2. I can extend this idea and I can think about the mth segment from the mth periodic signal and multiply this with a gate centered around spaced by empty units. Now, if I look at x t, x t is built up of various segments. So, x t is built up of these segments. The total signal is composed of these segments, where m takes in all possible values. Then I can substitute the value of x m t here and I can get the expression of x t which is this. And each periodic signal, this one, can use Fourier series representation. So, if it is a periodic signal, I can think about this periodic signal by the Fourier series expansion, and I can think about this in this way. So, first I had only a case, but now I have a case and there is an additional subscript m, and this m tells me that these are the coefficients corresponding to mth periodic signal. Okay. So, each periodic signal will have different coefficients and each periodic signal will have k coefficients, right. So, to tell about for which signal, which periodic signal these coefficients belong, we need to have this additional subscript. So, plugging in this value of x m t in this expression, what we have got is x t is nothing but summation m summation k. So, this is a double sum a k m e to the power j k omega naught t rect t by t minus m, and this is known as t spaced truncated sinusoid expansion. Okay. So, first of all, these sinusoids are truncated by this gate function, but these sinusoids are also t spaced truncated, right. So, this gate that is truncated the sinusoids is t spaced. Okay. So, let us revise and recap what we have said. We have just finished learning about t spaced truncated sinusoid expansion, where we have been able to express a signal as a double sum of orthogonal expansion, where this orthogonal functions are t spaced truncated sinusoids. And if we want to obtain this a k m, of course, you can simply obtain them by taking the inner product of x t with these orthogonal functions and dividing by the energy of these orthogonal functions, which you can quickly prove yourself that this is also going to be t. Okay. Let us now learn about discrete time Fourier transforms or DTFT. Discrete time Fourier transform is time frequency dual of continuous time Fourier series that we have just seen. So, we know that continuous time Fourier series expression can be conveniently obtained, as we have already seen, by having the Fourier series coefficients multiplied by truncated sinusoids. So, this is the expression of continuous time Fourier series, and we can obtain the expression of discrete time Fourier transform by using this idea of time frequency duality. And what is that? So, because of this property of time frequency duality, I can replace this t with f, I replace this capital T with 2 w, I replace e to the power j with e to the power minus j, and by carrying out these replacements I can go from continuous time Fourier series to discrete time Fourier transform. Also we can see that because omega naught is 2 pi by t, and we have already said that t should be mapped to 2 w. So, omega naught becomes 2 pi by 2 w, which is pi by w. So, let us see what would be the expression of discrete time Fourier transform. So, first let me write again the expression of continuous time Fourier series. And let us now carry out the replacements that I suggested. So, changing t to f. So, we go from a time domain signal to frequency domain signal. The a k's are replaced by b k's. So, a k's are the coefficients here. Let us assume that for dtfs or dtft the coefficients are b k. Then changing j to minus j, k remains k, omega naught gets mapped to pi by w, t is mapped to f, rectangular function remains rectangular function, t is mapped to f, and capital T is mapped to 2 w. And this is the expression of discrete time Fourier transform. So, let us first understand the obscurity when we are saying that T is getting mapped to 2 w, and let us try to understand why is there a factor 2 here. So, for example, when I say that a signal is limited to t duration in time, it can mean that signal exists from minus t by 2 to plus t by 2, and the total duration of the signal is t. So, this is the meaning when you are saying that signal is limited to t duration in time. However, when we say signal is limited to w hertz in frequency, other way to say this is signal is band limited to w, it means that the signal occupies w hertz only in the positive side of the spectrum. So, signal might have spectrum like this. So, w only denotes the occupancy of the signal in the positive side of the spectrum, and the total support of the signal is 2w, and hence when you say that signal is limited to t duration in time, it denotes that the total duration of the signal is t in time. But when you say that the signal is limited to w hertz in frequency, it means that the total duration of the signal is 2w in frequency, including positive and negative side of the spectrum. So, hence because of this notations, t is getting mapped to 2w. So, let us write the expression of discrete time Fourier transform again. So, we have said that in discrete time Fourier transform, you have an expression like this, and remember that this expression is valid for a signal which is band limited to w. And if I start from this DTFT expression and I take its inverse Fourier transform. So, let us start taking the inverse Fourier transform of this expression. So, xf will become xt, bk's remain bk's, and then we have to take the inverse Fourier transform of this. So, let us first try to see what is the inverse Fourier transform of this expression using the properties of signals and systems. You must know these relationships. For example, the inverse Fourier transform of a rectangular pulse is a sinc pulse, and if I multiply this rectangular pulse with a rotating complex exponential, then what happens is the independent variable in another domain gets shifted by a certain quantity. For example, in this case this would be shifted by k by 2 w. So, that is the effect when you multiply a function with a rotating complex exponential, the variable in another domain gets shifted. Okay. So, here the variable t will get shifted, and it will get shifted by this factor of k by 2 w. So, what we are saying is we have started with this DTFT expression, we have been trying to obtain the inverse Fourier transform of this expression, and now if I complete the inverse Fourier transform, I can complete it like this. So, what we can see here is, because these functions are orthogonal, this is a set of orthogonal functions. You can prove that this is a set of orthogonal functions using the same approach as we have used in the case of Fourier series. This is actually truncated sinusoids, and truncated sinusoids we have said is the set of orthogonal functions. Now, if this is a set of orthogonal function, can we say something about the set of these signals where the set is obtained by changing the value of k's, and remember the k belongs to the set of integers. And if we use Parsable's theorem, let me first write Parsable's theorem. So, Parsable's theorem states that x t into y t conjugates integration from minus infinity to plus infinity is nothing but x f into y f conjugate d f's integration from minus infinity to plus infinity. And what is this? This is the inner product of the signals in time domain. And what is this? This is the inner product of the signals in frequency domain. And remember, here x f is the Fourier transform of x t and y f is the Fourier transform of y t. So, what we are saying is, when you are transforming the signals from time domain to frequency domain, the inner product between the signals do not change, inner product is preserved. If inner product is preserved, it will also imply that orthogonality will also remain preserved. Okay. So, what we are saying is phi k f, that was the set of orthogonal signals used for orthogonal expansion in the case of DTFT, and if we take the inverse Fourier transform of these functions, we get a set 2 w sinc 2 w t minus k, and because this set is an orthogonal set, this set of functions is also orthogonal set, and this is because of Parsable's theorem. This is because when you go from time domain to frequency domain or frequency domain to time domain, the inner product remains preserved, and thus the orthogonality of the functions also remain preserved. So, let us now rewrite the expression for inverse Fourier transform of DTFT, and we have said that this is nothing but now let us do something in here. Let us substitute t as MTS and let us see what happens. So, this x t becomes x MTS summation k b k 2 w sinc 2 w t becomes MTS minus k. And as I have said, we want to map this T s to 1 by 2 w. That means, we are saying that if I am having this T s as we will see is also known as sampling period. We are choosing a sampling period same as 1 by 2 w, and this follows from Nyquist's sampling theorem. So, why is this sampling time like this? We will see in a while, but let us just see that what happens if you choose this sampling time as 1 by 2 w. Let us see what happens. So, if I choose T s as 1 by 2 w, we can also see in here this 2 w cancels with this 2 w, and the expression that we get is XMTS summation bk's 2w sinc m minus k. And let us now try to see what is this function sinc m minus k. So, sinc m minus k, by using the definition of sinc, the definition that is normally used in the courses on communication system is sinc theta is sin pi theta by pi theta. This is also known as normalized sinc function. So, if you choose this definition, this is known as the definition that is known as normalized definition for sinc function. Let us do not worry about all this. Let us say that we define sinc theta as sin pi theta by pi theta. In that case, sinc m minus k becomes sin pi m minus k by pi m minus k, and let us now substitute this m minus k as n. M is an integer, k is an integer, and this n is also an integer. So, I can think about this in this way, sin of pi n by pi n, and we know what is the sign of pi n by pi n. So, the sign of pi n by pi n, if n is 0, this takes 0 by 0 form, and then we can use L'Hopital rule and obtain that this will be 1, and if n is not 0, then this is going to be 0. So, using this relationship in here, we see that when m is not same as k, this term will vanish and there will be no contributions in the summation of the coefficients other than when k is same as m, and hence we can simplify this summation to just one term where the contribution will be only from Bm, because all other coefficients will become 0 because of this multiplication by sinc. The sinc is 0 for all k's when k is not same as m. So, there is only a contribution from Bm. So, we write XMTS is same as Bm times 2w, and you can see that Bm can be written as XMTS by 2w. So, now let us substitute this value of Bm in the original expression. So, we have said that xt is bk 2w sinc 2w t minus k, and substituting bk as xkts by 2w, the expression that we get is summation xkts by 2w into 2w sinc, and we can also substitute this 2w as 1 by ts. So, this becomes t by ts minus k, and we get the resultant expression as xkts into sinc t by ts minus k. And this is a very celebrated expression. It goes by the name of sampling theorem. So, let me write this expression again. So, what we are saying is xt is summation xkts sinc t by ts minus k for all values of k. Now, let us try to understand what this expression means. For example, let me assume that I have a signal x t. What is this x k t s? X k t s are the samples of this function collected at an interval of T s. So, if I have, this is at my time axis, if I collect the samples of this function at an interval of T s, these samples are x k T s. So, what this expression says is I can go from the samples to the signal by putting sinc caps around the samples. For example, let us assume that I have got certain samples, and if I start putting the sinc caps around these samples. So, sinc is a function like this. So, let me assume that I am putting sinc caps around these samples, and I sum up everything. When I sum up everything, I hope to get a continuous function. This function is x t. These black lines are the samples and these red functions are the sinc caps. So, this expression x t is summation x k t s sinc t by T s minus k states that if you put the sinc caps around the samples, you get the waveform, and this is a very important result, and it goes by the name of sampling theorem. Okay. So, why this sampling theorem is very important is when we will see the random processes and noise, we will see here that you can express noise again exactly in the same way. If you start putting the sinc caps around a random variables, then you get to random processes. There also we use this idea of sinc expansion of a signal. When we will go to this regime of modulation, there also we see that if you are trying to understand about the waveforms, you can start thinking about the waveforms by putting these sinc caps around the samples of the waveform. So, this idea, this equation is pretty useful, and we will use lot of it in random processes and modulation. So, what is remaining is trying to understand double sum orthogonal expansion using DTFT, which is exactly same thing as we have done in the case of Fourier series, and we have done a double sum expansion there. So, we will see about this double sum expansion in the next lecture. Thank you.